how do we construct this hand? We only want hearts, so that means we're going to have 13 choices for the first one, because there are 13 hearts, which will leave 12 for the next one, 11, 10, and 9. And once again, we overcount by 5 factorial. Okay? And so the answer is 13, choose 5. You could have thought about that more straightforwardly. We have 13 hearts, and we're trying to choose 5 of them. So 13, choose 5. How many hands are flushes? That's a little bit different, right? All 5 cards have the same suit. So now we're looking for how many hands have only hearts, or only clubs, or only diamonds, or only spades. So in this case, we're going to start with 52 choices for the first card. But once we choose the first card, the suit is going to be set, right? If we get an ace of spades, we're going to only want spades for the rest of the other 4. So that means there are only going to be 12 choices for the next one, because there are 12 cards remaining within that suit that we have already chosen on the first card. That's 12, 11, 10, 9. And we overcount by 5 factorial once again. And so you could write this as 52 times 12 times 11 times 10 times 9 divided by 5 factorial. Simplifying is not necessary. But this is also 4 times 13, choose 5. Right? Obviously, our answer should just be 4 times the answer for B, because now we're also asking how many hands have only clubs, or only diamonds, or only spades. And so it's just going to be 4 times 13, choose 5. Okay, question D. Now we're only interested in 2 card hands, so not 5 card hands anymore. How many 2 card hands are pairs where both cards have the same rank? Okay, so once again, we have 52 choices for the first one. But once we've chosen the first one, we want the second card to have the same exact rank as the first one that we chose. And so there are only going to be 3 choices, right? If we chose the ace of spades for the first card, for the second card, we're only going to want the ace of diamonds, or the ace of clubs, or the ace of hearts, right? And once again, we overcount by a factor of 2 factorial. So the answer is going to be 52 times 3 divided by 2, which is 26 times 3, or 78. Question E. How many hands are full houses? How many hands are full houses? Okay, this one is very tricky when it comes to how you account for overcounting. So I'm going to start by constructing this hand in such a way that I have my 3 of a kind here and my 2 of a kind here. Okay. Right, hopefully you know what a full house is. It's a triple with a double. I'm going to make sure that the triple is in the first 3 cards and the double is in the last 2 cards. This is going to affect how I do the overcounting. Okay, so I have 52 cards for the first, 52 choices for the first card. But then once I've set that, I want to make sure the next card and the next 2 cards have the same rank as the first one I chose. So that means I'm going to have 3 choices for the second one and 2 choices for the third one, because I want to make sure that I have the same rank. And so there are 4 cards per rank, so that's 3 and then 2. Okay, how many choices do I have for the 4th card? Well, I want to make sure I don't have the same rank as the first 3 of a kind. So that means I have 48 choices, because I want to choose one of the other 12 ranks, of which there are 4 of each. Okay, and then for the last card, I want to make sure I have the same one as that rank, so that'll be 3 choices. Okay, how much am I overcounting by? I'm going to be overcounting by a factor of 12. And the reason is because I've stipulated my 3 of a kind to be here, and I'm going to overcount by 3 factorial on that one. And then on the 2 of a kind, I'm going to be overcounting by 2 factorial. And so the answer is 52 times 3 times 2 times 48 times 3 divided by 3 factorial times 2 factorial. It's greater than 1,000. Okay. Yeah. Hopefully it makes sense why you're not dividing by 5 factorial. Okay, let me try to make it more clear. Okay, it's not 5 factorial because there aren't 5 factorial ways to actually rearrange one of these. Right, suppose we had jack, 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 queen, queen. Okay. The thing is, I specified that I only wanted arrangements that had the triple in the first 3 and the double on the last 2. So that means this arrangement, something like this, if I rearrange this into this would have never been possible in the first place. So I don't need to account for that kind of overcounting. The only kind of overcounting that I need to account for is the arrangements, is the, scrambling of jacks and queens within the triple or within the pair. Right, so this was J1, J2, J3, Queen 1, Queen 2. I'm only accounting for this kind of overcounting, right? If I had rearranged it to be J1, J3, J2, or Queen 2, Queen 1, right? I'm only considering those. And the amount of those is 3 factorial times 2 factorial. Hopefully that's clear enough. F. Very similar. How many hands contain a 4 of a kind? Okay, so remember, this is a 5-card hand, and we're asking how many of them contain a 4 of a kind. So once again, I'm going to specify that the 4 of a kind is in the first 4 cards, and then the last card will be the kicker. That's what it's called in poker. You can just think about it as a card with a different rank. All right, it has to be a different rank because there aren't any left. We took all 4. So I'm going to have 52 for this one, then 3, then 2, then 1, then 48 for the last one. Very similar to the previous question. Then how much do I overcount by? I'm going to overcount by 4 factorial. Okay, so the answer is going to be 52 times 3 times 2 times 48 divided by 4 factorial. Now, bad news, I think this is less than 1,000. Sorry, I had to respond to a message. Okay, 4 factorial is 24, and so that's going to leave me with 2 in the numerator. So the answer is 52 times 12, which is 624. Just checking this. Okay, what do I have next? Diagonals. I enjoy these questions. There's a nice trick to this. Okay, number 6. How many diagonals are in a square? Not a trick question. I'm just trying to set up the whole thing. A square has 2 diagonals. Okay. How many diagonals are there in a pentagon? Oops, that's not a pentagon. Pentagon. How many diagonals? I should specify that it's a convex pentagon, but that's implied. The diagonals form a star. What happened? 2, 3, 4, 5. That's 5 diagonals. Number 8. How many diagonals in an octagon? Wow, I don't know if I want to count them. The answer is actually 20. How do I know it's 20? It's because I know the trick. I'm going to count them all just to prove it to you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, there it is. There's the 20th one. Okay, so the answer is 20. All right, how do we do this for bigger and bigger numbers? That's the challenge. All right, here's the trick. Here's the trick. Think. How do you construct a diagonal? How do you construct a diagonal? Answer. 2 vertices. You choose a diagonal by choosing 2 vertices. Right? Wow, I used the word choose. What could that mean? The thing is, it's a little more subtle than that. It's not just going to be n choose 2. Why is that? This is an awful diagram. Let me make this more clear. Let me label the vertices in red. Okay. A diagonal consists of 2 vertices, but the vertices cannot be adjacent. So let's look at this. Let's say this is my first vertex, second vertex, right? I'm going to think about the buckets. How many choices I have for each vertex? First vertex, second vertex. Okay, now I have an n-gon, right? So an n-gon means that I have n total vertices and n sides. So for my first vertex, I'm going to have n choices. I can choose between any of the n vertices to choose for my first vertex. Now for my second vertex, how many can I choose? It's not n minus 1. All right, let's say I choose this one. Let's say I choose this one as my starting one. That means I should put this in green, right? If that's my starting vertex, then my second vertex, what are the restrictions on the second vertex? It can't be the same vertex as the first one, but it also can't be the ones next to it, because those won't form diagonals. Those are just going to form side lengths. It has to be one that's not the same and also not adjacent. It could be this one, right? That would give me this. It could also be this. So it could be something like this. So it could be any of the n vertices except for itself and the ones next to it. So that means I have n minus 3 choices for the second vertex. And then finally, am I going to be overcounting? Yes. The reason is because a diagonal is the same no matter what order you choose the vertices in. Right? So if you choose this one first and this one second, it's the same as if you had chosen this one first and this one second. And so the answer is going to be n times n minus 3 times 2, divided by 2. And you can confirm that's true for a square, a pentagon, and an octagon. Hopefully that's an interesting question.